Welcome to our P.D training video on optimized thickness bolus construction. So as you can see, I have P.D open and I have the ECT chest wall patient provided by Dot Decimal loaded into the software. If you have not yet worked on loading a patient into P.D, please refer to the help manual specifically for that task. Also, when loading this patient, you will need to have selected the Dot Decimal example machine. If you have yet to set up this machine, please see the video that guides you through setting up machines in P.D. Okay, so we're going to go ahead and begin our bolus construction by entering the bolus wizard. So once we've opened the bolus wizard, we're going to select the default option here, the optimized thickness bolus. This is probably the most common option, so this is the default in P.D. Alright, then we're going to go through now and we're going to select each of these parameters that we need to design our particular bolus. So we've already selected the decimal example machine when we loaded this file, so that is chosen for us. We need to select the type of CT scanner that these images were generated with. So for this particular patient, it was 120K, not 140K scanner. Then we need to select the beam over which we're going to design the bolus. In this case, there's only one beam, so beam 1 is selected. We need to select the treatment energy for this particular tumor. Well, remember, these energies correspond to those that are defined in the decimal example machine. And we also see, in case we forgot, the energy from our treatment planning system, okay, that was specified and passed to P.D through the DICOM file, is given here. So this was designed in the treatment planning system for an energy of 12 MeV. With the bolus, we want to be able to go just a little bit thicker here, so we're actually going to go ahead and select a 16 MeV beam to treat this particular patient. Okay, then we need to select our body and our target structures. So remember, if P.D sees something with the word external or body or patient or skin, it's going to try to select that by default for our body contour. Okay, that defines the outside surface of our patient. So we only have one contour that has any of those keywords, and that is the correct one that P.D has selected for us here. So when naming your contours, your structures in your treatment planning system, if you use those keywords, you will find that they get automatically selected by P.D. Save yourself a click or two. The target, well, in this particular case, there's a couple things that might be worthy to be the target. We have the GTV, we have the PTV, and then we have test PTV. We're going to use the PTV. If you want to try this tutorial, going through this similar one on your own after this is completed, the test PTV is another one that will give you an opportunity to see if you can design a bolus on your own. Alright, so we're going to utilize the PTV, and again, P.D selected that for us because of the name. It'll also try to select things with the keywords of tumor or target included in their names. Once we've selected those initial setup parameters, we're going to go ahead and click Next to go to our patient side surface page. Well, there's a training video specific to the patient side surface. Remember, the patient side surface is important because we want to make sure we minimize any air gaps between our bolus and our patient. Air gaps can sometimes increase the skin dose that the patient receives, so we want to try to make sure we have a bolus that fits very well to the patient's surface, does not obstruct or does not cause any discomfort to the patient by jutting or protruding against their skin a little bit. So we want to make sure that we have a good fitting bolus. So spend a little bit of time making sure the surface construction is good. Make sure that your patient contours are nice and smooth and represent your patient very well. So for this particular case, we're just going to go ahead and drop the block outer border down to 0.5 cm, and then the rest of the default parameters are okay. We shouldn't really need any smoothing for this patient because the external contours are already pretty smooth and pretty well drawn for this particular patient. Alright, once we've got our patient side surface, I'll point out a couple things real quick. Notice that there's a little flat spot in our patient side surface here. The reason is this is because our depth beyond target has been limited to 0.5 cm. If we're not comfortable with how close the edge of this tumor is to the edge of the bolus, we could go ahead and decrease this and bring this down. But for this particular case, this will be enough for us to get the dose that we're looking for at our tumor. So if you have a case where this is a little bit closer up to the tumor, you may want to decrease the depth beyond target a little more to make sure that your bolus extends far enough beyond your target. Alright, so we can go ahead and click Next to bring us to our proximal side surface page. Okay? Remember, the proximal side surface is what gives us control over the thickness of the bolus. By developing the right thicknesses of the bolus, we're going to be able to get good conformality between our prescribed dose and the back of the tumor volume. So in this case, what is our prescribed dose? Well, that's the first parameter that we select. Typically, the default value of 90% is going to be what most users select for their distal PTV dose. Remember, this distal PTV dose is normalized relative to the case of a standard slab water phantom. So if we had a slab water phantom with this energy incident on it, we find the location of Dmax, that is considered 100% dose. So that is what this is normalized to. And that's at a SSD of 100 cm. Okay, so a discussion of that normalization can be found in a little more detail in our help guides for those of you who are interested. So we're going to have our distal PTV surface match the 90% line. Most of our operators rely on having a consistent normalization, so we try not to use a normalization in P.D that moves, that is, say, the field max or a particular dose at a point in P.D. We avoid that because most of our design operators rely on having a standard location of normalization. They work much more effectively with a normalization that is consistent throughout the design process. Okay, so this first drop, or this second drop down here, is what we call our bolus design operators. Okay, each of these bolus design operators allow us to do or allow us to create a slightly different bolus design. We're going to see the automated marching and these first three sequences are very common to use. After these sequences come the individual operators. These individual operators can be applied if you have some experience, if you have some idea of exactly the steps you want to take in designing your bolus. So those of you that are familiar with this process, you might be able to design a very good bolus pretty quickly by applying the operators in the order that you desire. The automated marching will give a very good first approximation to the bolus results. Sometimes these results will give you exactly what you need right out of the gate. Sometimes you may have to apply a couple extra operators to get them to just tweak those last little clinical goals that you are looking for in your particular patients. The geometric single shift and double shift, these all build on each other. The geometric is contained within the single, just adds one more step. And then the single is contained within the double, it just adds one more further step. Okay, we'll see these operators as we go through the rest of this video today. So let's begin with the automated marching. We can leave the default values here. And we're going to go ahead and click generate. And while this is going, we'll talk about a couple other features in P.D. So we're going to see that this automated marching process is going to go through a few dose calculations. Okay, it's going to go through about between 10 and 20 steps, depending on how much hotspot damping you select. It's going to go somewhere between 10 and 20 steps in computing our bolus. So this could take 10 to 15 minutes, depending on the speed of your computer and the size of your field. And what you'll notice here is the marching actually started from a flat top bolus. And what the marching process does is it's going to say, well, in pretty much everywhere in this tumor, except for maybe one location, we're going to see that the 90% line here, shown in yellow, doesn't really reach the back of the tumor, except for maybe at a couple spots. Everywhere where the 90% line is still above the distal surface, we're going to decrease the bolus thickness in those locations. That's what the marching process is doing. So we can see most of the surface locations, except for right here and right here, have decreased with each marching step. And we see the results are changing because every time a new marching step is completed, P.D shows us those latest results. And we can see after a few steps, we're already starting to get good regions of the bolus to conform to the back of the tumor. And we can also see that, well, while some regions start to conform, the hill that's generated by the other ones leaving behind kind of cause our dose to pull up, create some little hot spots. So we're going to notice that in addition to the marching of the bolus downward, if we look in our operator history here, okay, we're going to see not only are we marching, that's each of these steps, but we also have some hotspot damping that attempts to reduce some of the high peaks of the surface, bring them down to eliminate some of the hot spots and some of the cold spots that appear in our solution. So once we get through the first few steps, we'll see that it's typically going to jump back and forth between a marching step and a damping step, unless we select a damping percentage is very high. Okay, so typically the smaller value of damping we select, the more damping we're going to get, the smoother bolus we're going to get. We won't get as good of conformality of our prescription line, but we'll get a much smoother result with less hotspots. Okay, so that is what our damp hotspots parameter will do for us. Basically tells us what's the maximum or what's the minimum dose that you want to see in your field for starting to damp hotspots. Okay, we start to see that we get pretty good conformality as we get into some of these later steps of our marching. Okay, and we start to see though that in a few areas we overshoot, and the reason we overshoot is because we're trying to damp out those hotspots. So as we damp out those hotspots, the only way to do that is to create a little bit of overshoot in our patient. We see a pretty good hotspot over here to the left, but we should also note that most of this hotspot is actually in the bolus, not in the patient. So most of this hotspot on the left here is actually only going to be depositing dose to the bolus, which typically is not much concern to us. Okay, so we're at step 7 of 10. We've got a couple more to go. While this is going, I'll point out one more thing. If we're not happy with what we're looking at as far as dose in P.D, we can click here on this icon next to the reference dose, and we'll see that that's going to pull up our dose display settings, and we can change the way the dose looks in P.D. So maybe I'm not interested in the 10% line. Maybe there's too much clutter here, so I'm going to take off the 120 and maybe just use a 115. Okay, so I'm going to go with 50, 80, 90, 100, 110, and 115 for this particular case. Okay, so we can remove some contours. We can change colors. So if we go back in here, if we want to change the color of any of these, we simply double-click the color. We can select a new color for those. If we want to turn them on and off, we've got the visible value. If we want to change their value, just go ahead and type in the new value. You've got a few placeholders to add some extra ones if you want as well. If you find the legends getting in your way, you can turn that off and on as well. And we also have some color wash settings. So if you want to see a whole dose field rather than just the individual ISO lines, you can turn that on as well. Okay, so we're on step 10 of 10, so we're going to probably have one more hotspot damping step, and then we should be completed with these dose results. And you'll notice here, what I'm looking at in that list is our operator history. So we can see our operator history throughout the bolus design process. And I can click on any of these solutions at any time, and P.D is going to send me back to that particular solution so I can view those results. So these are the bolus results and the dose field at step 6 of 10. I'm field 10 here. So I can look at different results at any time without affecting my solution. My solution will continue to calculate while I'm looking at those results. Okay, so maybe we want to compare what's going on. Remember, we said we started with that flat top result, and then we kind of saw that the bolus slowly marched down as we go through the marching process. And we can see if we look at maybe step 11 here, by the time we get to step 11, we've got pretty reasonable coverage of most of the bolus surface. We see maybe this little pulled up region here, but the difference between our 80 and our 90 isn't so great, and it's probably still in the 87, 88 range right in here. We could change our contours if we wanted to look at that as well. So then if we look at the end, we're going to see that there really isn't much change in the distal coverage between these two. Okay? But we see that the hot spots are going to be a little bit reduced in our later case between these last few. So you're going to see when you do the marching that most of the marching happens in those first maybe half of the steps. And then after that, it's pretty much just trying to damp those hot spots and get us a slightly more reasonable solution without having such high dose values in our field. All right, so if at any time you scroll through a solution, maybe let's take a look at solution 17 here. If at any time you decide that, well, you know what, after reviewing this solution, I think the solution to 17 is a little bit better than my final results here at 19. So if I like 17 better, all I have to do is tell P.D to roll back to that solution. So I go ahead and click rollback. It's going to close my history, and it's going to set 17 as the most recent bolus. Okay, we close that history just to let you know that something happened there. You'll see that 17 is now marked with an asterisk. We've got a little star in front of 17 because that is our active bolus. If we were to perform any more operators, they're going to try to build off of dose 17, not of dose 19. If we went ahead and clicked finish here, it would select the active bolus. It would take 17, not 19. Okay? So that's our automated marching operator. So hopefully you have a good understanding of how that works, what the results are, and how to roll back to any of these steps at any time. All right, so what we want to take a look at now, these next three sequences, we're actually going to see that if we run the double shift, it actually contains a geometric and a single in it. So I'm going to go ahead and run the double shift. It only takes maybe a minute longer than the single shift. So I'm going to go ahead and run that. And you're going to notice that we get this warning that pops up. And what this warning tells us is that our previous results are going to be ignored. And what that means is, it doesn't mean we're going to lose any of these. It doesn't mean we're going to delete any of these. It means that this double shift sequence actually contains in it a creation operator. Okay? Many of these operators in P.D are what we call creation operators. If they're a creation operator, it means it has all the information it needs to develop its own bolus from scratch. Okay? Which means regardless of what I've done previously, when I run an operator that has a creation sequence, it's going to start a fresh bolus. It doesn't matter what I've done previously. It's going to make a new bolus, and it's going to completely ignore anything I've done up to that point. But you'll also notice I haven't lost any of my history. So if I want to roll back to any of these, it doesn't matter that I now used a creation operator because I can roll back to the other ones at any time. But what it does mean is if I wanted to see just the double shift sequence, it doesn't matter that I've already run the automated sequence. I would get the exact same results if I just opened P.D and ran the double shift sequence. The fact that I've already run the automated sequence makes no difference to running the double shift sequence. Okay? So that's what we see that warning in P.D. Okay? So we see we got 3 new entries in our history. We've got the create and smooth entry, which is actually pretty much exactly what we'd see if we did the geometric sequence, except for it would also be truncated. All right, and then we see the isodo shift and smooth. This is what we would get if we ran the single shift sequence, and then we see another isodo shift, another smooth, and then we see at the end this truncate. So when I click on this, notice that the height of the bolus here, these little wings at the top here, is going to reduce significantly when I click that last one. Okay, that's what our truncate operator does. It cuts off that excess top of the bolus that we don't really need. Okay, we keep that there while we do the isodo shifting just because it allows us to shift upward if we need to. The marching operator, remember, will only decrease the height of our bolus. It never tries to go back up. Okay, the isodo shift operators, however, they will go up or down depending on what's needed for the field at those particular times. So typically, we like to apply the truncate if we're going to. We do that as the very last step of the process. So you'll notice that this isn't exactly the geometric sequence. If I were to truncate from here, I'd get the geometric. This isn't exactly the single sequence, but if I were to truncate from here, I'd get the single shift sequence. Okay, I truncate at the end when I'm planning to use the manual operators or these sequence operators. So these 3 results, in this particular case, they may not be quite as good as the results from the automated marching case. Okay, the hot spots are a little bit higher, and the cold spots are a little bit higher or a little bit worse for these particular operators. Now, this isn't an across-the-board thing. Sometimes the double shift sequence gives us better results. Sometimes the automated marching gives us better results. It all depends on the specifics of your particular patient, the heterogeneities, the slope of the patient surface, the energy that you're treating with. There's a lot of different factors that go into which one gives us a better solution. And oftentimes, it simply boils down to the shape of this distal PTV. All right, this particular PTV has a lot of rapid changes in the distal surface. If this were contoured a little more smoothly, if this tumor was a bit more smooth, we would see that this double shift sequence would do a great job of designing this particular bolus. Okay, so I ran this. I don't really like it. I'm going to go ahead. I'm going to roll back to 17 because I think that was probably my best solution so far. So I'm going to click on 17 and I'm going to roll back to get us back to that particular solution. All right, and well, I'm still not quite happy with this solution. I know there's quite a bit of overshoot on this slice, but there's not much we can do about that because we're trying to reach the deep part of this tumor here. So if I sacrifice this overshoot, I'm going to end up with underdose here with too low of a dose at this peak of the tumor on this slice. So that's why we kind of see the overshoot on the isocenter slice, because a couple slices later we have that very peak deep spot of our tumor. All right. Well, what I'm not really happy with in this plan, I don't like this 115 hot spots here and there. So what I want to try to do is use some of our single operators here to reduce that a little bit. And usually the best one for reducing those hot spots is the smooth operator. All right. And these smoothing weights, the weight and the size, help to control our smoothing. All right. We're going to do exponential smoothing, and the exponent is negative, so as I make this smaller, it's going to create more smoothing. In this particular case, I'm going to need quite a bit of smoothing to get rid of these hot spots, so I'm going to drop this down to about 2, which is a very small value for this. And the size factor tells us how big of a spread we want on our smoothing. I'm going to increase this a little bit just to a factor of 2. And then I'm going to go ahead and click Generate Bolus, and I want you to pay attention to this 115 hotspot here and see what results. So we've already done the smoothing. We're recomputing the dose field now. And we're going to see here that our 115 is pretty much gone. All right, there's a little tiny 115 there, but it's significantly reduced from where it was previously. All right, we still get our peak covered. All right, if we pull out our history here and we look at 17 and this one, we see very little change in the 90% line. Okay, the smoothing kind of smoothed it out a little bit here, but overall our conformality hasn't really been too affected by the smoothing in this case. All right, so we see that hotspot got significantly reduced here, but we didn't sacrifice much in terms of conformality. So this is going to be a much better solution here. Maybe I still want a little bit more smoothing. So I can try again, or I can roll back to 17. So I'm going to go back to 17 and roll back. Okay, I wasn't happy with that smoothing. It didn't quite give me what I want. So I'm going to try even more. You'll see the lowest value P.D lets you go here is a smoothing weight of 1. I'm going to try a 1 and see if I can get rid of that hotspot altogether here. So I'm going to generate my bolus. I'm going to see if I can get rid of this hotspot altogether. So I rolled back to 17, and then I'm going to try to reapply the smoothing from 17. You can also smooth, working on the same one if you want as well. So whichever way you prefer, it doesn't make a whole lot of difference. It's just a matter of preference, whether you want to try to do it all in one shot by rolling back, or you want to do it using increments. All right, so I see my 115 is completely gone now by using this smoothing, but maybe I hit a couple little cold spots here. Okay, so maybe I missed just a little bit of my tumor in these particular regions. So we have one more operator we'll take a look at real quick. That's our specified shift. So if we really like this dose, but we're just not quite happy with this little miss here, what we can do is we can zoom in here, and I can kind of measure how far that is. So remember, if we right-click, we have a distance measurement tool in P.D, and we can see that's maybe 3 millimeters, 4 millimeters. Okay, so I'm going to try making my bolus maybe 2 millimeters thinner and see if I can get a little bit better coverage. All right, so I'm going to click Generate Bolus, and that's going to shift my entire bolus surface down by 2 millimeters. That's a negative value. It's going to make it thinner by 2 millimeters. And we're going to see that that's going to help us cover this area a little bit better. So there we go. I like the 2 millimeters. I don't want to go much more. I think that little bump may just be an artifact in my contours. That may not be physically there in the patient. So now there's pretty good coverage of our tumor. We've seen how some of these different operators act. If I need to spare this a little bit more, and I think that maybe this peak just isn't quite right, I can shift upward. So if I wanted to change this and shift upward, I can shift my whole bolus thickness upward a little bit. If I need to smooth out more hot spots, I can reapply smoothing. If I want to try some other sequences, I can try starting again. If I'm ever unhappy with anything I did, I just click back to where I was happy, and I click roll back, and now I'm back to that particular bolus results. Okay. The one thing we need to be careful with when we finish, notice highlighted in orange is what's displayed on the screen. But the one with the asterisk is the one that's actually the active bolus. This is the one with the asterisk is the one that we will actually accept if we click finish. It's the one that we will actually modify if we click generate. And notice it won't even let you click generate if you're not selected on the active plant. Okay? You can, however, finish if you're not selected on the active plant. So when you're clicking finish, make sure that you understand you might not be looking at the actual results that are going to be selected. Okay? So we're going to go ahead, we'll click on our active plan here, and we'll go ahead and we'll click finish because this results look pretty good for this bolus design. Okay, so we can review those results one more time, scroll through them if we would like to look at them. We'll notice our bolus is now saved here in the tree view, and our reference dose is here as well. We can turn those on and off just like we can with any other structure at any time. And if we want to modify the way the dose looks at any time, we can double click on that and pull back up our dose display settings. So that's not limited just to the Bolus Wizard. Anytime you're in the tree view with a reference dose, you can click on that reference dose and take a look at that value as well. If we want to see what our bolus looks like, we're not going to see any dose in 3D, but we can see our bolus design here. I'm going to turn off the beam and the block. We can see our bolus surface here. That smoothing that we did made our bolus look very nice and very smooth because that was a very large value of smoothing that we applied to this bolus to kind of reduce some of those hot spots. So not all boluses will end up looking this pretty and smooth. The reason this one is because we applied a very heavy smoothing to that bolus surface to try to remove those hot spots. Okay? So we've got our final bolus design. We're now ready to send this back to our TPS, do our final dose calc, and review. Remember, P.D is displaying dose, but it's displaying dose that's for reference only. This has not been commissioned for a particular machine at your clinic, so please make sure that you're going back to your treatment planning system and that you are reviewing your dose field and accepting your plan based on the dose results from your treatment planning system.